Here are solutions to homework set number 10 for ECE 461-661 control systems. This homework set looks at z-transforms and converting from the s-plane to the z-plane. Now the first problem is if I have a transfer function in z, what's the difference equation relating x and y? Now what we did before is have transfer functions in s. S is the Laplace operator, s means derivative. Z means next value for difference equation. So the trick here is multiply out the polynomials, cross multiply, and then note z means next value. So z cubed y is y 3 samples in the future, z squared y 2 samples in the future, next value, current value, and likewise for x. So here's the difference equation that corresponds to this transfer function. Some people don't like using future values, so just do a change in variable, shift everything by 3, and I can also write the difference equation this way. So here I'm using the current and previous values. Either one's correct, just difference by a change in variable. Problem 2. Suppose I have this difference equation relating x and y. What happens if x is a sine wave? What's y? Well, to do that, that's phasor analysis. In phasors, s equals j omega, so s is j3. Z is e to the st, so it's 1 at 0.3 radians. X is 2 minus j4. In phasors, real part's cosine minus j is sine. So plug it in. Plug in z up here, plug in x, multiply it all out, and get a complex number. What that means is the real part's cosine minus j is sine. Problem 3 says what happens if I have a step input. In this case, that's actually z-transforms. Take the z-transform of x, which is z over z minus 1, multiply by the gain, I get y of z. Now this is not in my table of z-transforms, so what I do is do a partial fraction expansion. Pull out one of the z's, do partial fractions, so there's something over z minus 1, 0.98, 0.95, 0.8. Find the terms using partial fractions, multiply it through by z, and here's your answer. This is 25 minus 45 times 0.98 to the k, plus 21 times 0.95 to the k, minus 0.74 times 0.8 to the k, for k positive. Problem 4. Suppose I have this system in the s-plane. What's the discrete time equivalent? There's a couple ways of doing it. The approach I like is mapping. Z is e to the st. So poles at minus 0.47, 3, 9, and 16 in the s-plane, map to the z-plane, and it's 1 for 1. 4 poles s-plane, 4 poles z-plane. Here's where the poles are in the s-plane, map is e to the st. Here's where the poles are in the z-plane. Add a gain k to match the DC gain. So the DC gain of g of s is 0.74. Pick k so that g of z also has a DC gain of 0.7048. Gives you k is 0.11. And optionally, to get the number of zeros at the origin, that's just kind of a phase shift. Add as many zeros as you need to match the phase shift. So to do that, pick your favorite frequency. I chose 0.1 radian per second. Here's the gain and phase shift of g of s. G of z should have the same gain, same phase shift. The gain's the same, that's what k did, but the phase shift is wrong. Every time I multiply by z, I'm going to be adding 2.86 degrees. That is just s is j omega, z is e to the st. Plug in s equals j.1, I get 1 at 2.86 degrees. So take that difference, and how many 2.86s make up that difference? So taking that difference divided by 2.86, I need to add 2.82 zeros at the origin. I can't do fractions. I can do 1, 2, or 3 zeros, so round to the nearest integer, 3. Whatever you do, it's going to be wrong. 3 is the least wrong answer. So that's g of z. To check your answer, let's take the step response. If the two systems are the same, they have the same step response. So here's g of z. Take the step response of g of z, find the step response of g of s, plot the two on the same graph, and here's what you get. G of z is in blue, g of s is in red, and if you notice, the blue line is a little bit too far to the left. That's because I took 2.8 zeros at the origin, rounded up to 3. So it's a little bit too far left. If I would have rounded down, it'd be too far to the right. That's about the best I can do. But essentially the same system. Same settling time, same DC gain, same shape, almost the same delay. G of z is basically the same as g of s. Problem 5. Repeat, same problem, but change the sampling rate. Same procedure. Here's my poles in the S-plane. Map as z to the ST. Here's the poles in the Z-plane. So there's where the poles belong. To find K, match the DC gain. So this is G of S. Find the DC gain of G of S over G of Z. K is 0.0045. Not uncommon to get really small numbers. This is basically how much the discrete time system changes in one sample. To match the phase shift, pick your favorite frequency, like a 0.1 radian per second. Here's S, T, Z. Find the angle of G of S at 0.1 radian per second. Find the angle of G of Z at 0.1 radian per second. How much is the difference? How many zeros at the origin do I have to add to make up that difference? I need to add 2.23 zeros at the origin. I can't do fractions, so round down to 2. If I plot the two together, here's G of S, here's G of Z. Plot the two step responses, and G of Z, if you notice, is a little bit too much delay, because I should have 2.3 zeros at the origin. I only have 2. So it's off by 0.3 zeros. Again, I can't really do that. Kind of stuck with integers. But again, same shape, same settling time, same DC gain, almost the same delay. Basically the same system. Next problem. Problem 6 is root locus. Suppose I took G of Z, that's my system with a sampling rate of 0.1 second. Draw the root locus and find K for critical damping. So when I draw the root locus, here's what it looks like. Here's my poles, here's the zeros at the origin. These poles come together, split apart, loop around. Here is critical damping, problem 6, problem 7, and problem 8. Problem 6, I choose the breakaway point. At that case, S or Z is 0.843. Find the gain of 0.843, it's negative, which means you're on the root locus. Gain isn't 1, pick K to make the gain 1. So there's K. Form the closed loop system. Here's G, K, closed loop system, and sure enough, I've got the poles at almost the breakaway point. And your step response to the closed loop system. In MATLAB, to plot the step response, I'm kind of stuck plotting the step response of G. What I really want to do is have a discrete time compensator, have a continuous time plant, put the two together. That's kind of hard to do in MATLAB. Vissim or Simulink will do it. MATLAB doesn't really do it that well. You could, but it would be kind of difficult. This is really what you're shooting for. You can see that U is discrete. The output G, or Y, is continuous. This is really how you implement it. I've got a discrete time system, discrete time compensator, driving continuous time system. If I do it right, I've got no overshoot. Poles are the breakaway point. If instead I want 20% overshoot, again, what I would do is, going back to the root locus plot, draw the damping line for 20% overshoot, find out where it intersects. That point is 0.86 plus J.2. The evaluating G of Z at that point is negative real. It says that point's on the root locus. Here's the gain that puts you there. Form the closed loop system with K is 5.59. And here's my dominant poles and fast poles. Take the step response, and it's 20% overshoot, like I expect. the way to actually implement it is a hybrid system. I've got K of Z and G of S. Put the two together, I should get 20% overshoot. Finally, if I want to find the max gain for stability, what I would do is go back to the root locus plot, draw the damping line for zeta equals 0, that's the unit circle. Where do I cross the unit circle? At this point, find K. Well, at any point on the root locus, G times K is minus 1. So find S, find K to make the gain minus 1 at that point. K is 23, so that should make you oscillate. Checking it, form the closed loop system when K is 23. Here's my closed loop poles, 2 on the unit circle and 2 elsewhere. Plot the step response, and you can see it's just oscillating. Or, better, if you could use Simulink, here's your K of Z, here's your G of S. Close the feedback loop. It is actually slightly unstable. It should be right on the J omega axis. A little bit wrong because the G of Z that I designed is a little bit wrong because I need 2.3 zeros at the origin. I can't do 2.3. If I make it 2, I am underestimating the delay in the system. So the extra delay makes it go slightly unstable. That is homework set number 10 for ECE 461.